Today, from this tutorial, I'm gonna discuss about subtractors. Subtractors which we use in logic gates. So these are generally employed for arithmetic and logic in computers to subtract as CPU and GPU for the application of graphics to decrease the circuit difficulty. So subtractors are mostly used in for performing arithmetical function like subtractors in electronic calculators as well as digital devices. So you see, today we have subtraction. We have to do subtraction and additions. So earlier I talked about additions. Now here I am going to talk about subtraction. How to subtract uh, two digits using these logic gates, these combinational circuits. Using these combinational circuits, how can we get output? How can we get the output using this combinational logic gates if we are subtracting two digits? So initially you can see there are two types of subtractors. One is half subtractor, the other one is full subtractor. So half subtractor is the half subtractor has a combinational circuit, right? So it which uses to perform subtraction of two bits. It only uses two bits for subtraction. Here you can see A and B are there. This is the difference between these two numbers. This is the difference between these two numbers. This is the difference. This is the borrowed one. When you are subtracting, sometimes you cannot subtract. Here you cannot subtract 0 minus 1. Because of that, think that there's imaginary one comes from here and it will come as here as a 2. So 2 minus 1, answer is 1. And you borrowed a 1 bit, no, that 1 bit to the base 2, the 1 bit, because you borrowed a 1 bit, you are putting 1 here, right? So 1 minus 0 is 1. You didn't borrow any bit from anywhere. 1 minus 1 is 0. Also you have no any digits borrowed. 0 minus 0, 0. You didn't bought any digit from the from here, from the next proceeding value, from here also, but in here you have borrowed the value. You cannot subtract 0 minus 1. In order to subtract, there should be a 1 here. In order to have 1, we are bringing 2 digit. Out of 2, if you subtract 1, answer will be 1. Because you have borrowed something from this space, you have to put 1 here. Because you have borrowed something. Borrowed a 1. Right? So this is the half subtractor, the logic circuit. This is typical XOR gate. This difference column. Okay, this is typical XOR gate. This is A bar B of a AND gate. A bar B column. A bar B column. If you take A bar and multiply with B, you will get this digit. If you multiply A bar and take B, you will get this digit. Right? Similarly, you can implement this one using Logism. So let me show you my Logism interface. So here you can see I have taken the truth table to here, and let me explain you this one again using this truth table. If you subtract 0 from 0, the answer will be 0. While subtracting, you didn't take any value from somewhere else. So because you didn't borrow anything, you will be putting 0 here. Then we are going to subtract 0 from 1. 0 minus 1, you cannot do. Therefore, imagine that there's a 1 here. You borrowed a 1 here from this space. You borrowed a 1 here. Because of you borrowed a 1, because of that, you will be putting a 1 here because you borrowed a 1. In order to subtract these two, you borrowed a 1. Because of the thing that you have borrowed, you have to put 1 here. because you have already taken one from someone. So one here, right, this one act as 2 because you borrowed one from the outside. One comes, when it comes to here, it's 2 because next proceeding value is base 2 to the power base, right? So here you comes 2. 2 minus 1 is 1 because of you have borrowed, it's 1. 1 minus 0 is 1. You didn't borrow anything from someone else in the outside or the next stage, it's 0. Here 1 minus 1 0, you didn't borrow. So this is the truth table. So this is act as a XOR gate, so I will directly taking XOR gate from here. I will make it as 2 inputs. Okay, and I'll take inputs like this. I'll take output, and again I need AND gate for this one to represent this differential borrowed column. I need AND gate. I'll be taking an AND gate and I'll be placing it in here. I'll be reducing the number of inputs to 2, and that NAND gate should be connected with the NOT gate because initially I told you this borrowed column is formed from A bar multiplied by B. A bar. In order to get A bar, this is connected to A bar. Right. This is A, this is B, right? I converted this as A bar and I need B. And I'll be taking the output. So I'll be putting some pins here by copying and pasting. My circuit is now almost completed. So with this I would like to take I would like to label this one. So this is my A gate, A input. This is E input. So when it comes to here, it acts as here B bar. And here I have the difference. Here I have the borrowed one. I have the borrowed value. I have completed my circuit. Then there's another thing here, subtract. Rather than using these logic gates, I can directly use this pre-created circuit subtractor and place it here. Reduce the number of inputs, number of digits as 1. Thereafter, you have inputs as A and B. You have inputs as A and B, and you have output this is the difference, and this output is the borrowed. So this one is the reference, this one is the borrowed. Right? I will name this one as This is my A input, this is my B input, this is my difference, and this is my borrowed one. So you can see this is my difference output, which we represent from this column, and this is the borrowed output, which we represent from this out. So I have completed using both circuits. So let me start simulating this one. Let's check whether the result is true or not. Right? So I'm choosing this hand tool. When the inputs are 0 0, output is 0 0. Inputs are 0 0. You can see inputs are 0 0, outputs are 0 0. No problem. When the inputs are 0 and 1, when A is 0, B is 1, A is 0, B is 1, A is 0, B is 1. So from the both circuit it is proved that output is 1 and 1, 1 and 1. Difference and borrowed both are 1. Third step, when the input is 1 and 0, when the input is 1 and 0, when the input is 1 and 0. From the both circuit it's proved that it's 1 and 0, 1 and 0, the difference and the borrow, 1 and 0 difference and the borrow. From this one, if the both inputs are active high, you can see it's 0 0, 0 0 from the both outputs. It means if you are going to subtract 1 from 1, the answer will be 0 and we have not borrowed nothing. Okay, let me take this one, 1 0, right? 1 0 instance. If you subtract 1 from 0, will be having remaining 1 and you didn't brought any value from anywhere. You have remaining 1, you didn't have brought anything from anywhere. So this is the process of subtract, a half subtractor. So let me move on to my full subtractor. So in full subtractor we have 3 inputs. So a full subtractor is a combinational circuit which performs subtraction involving 3 bits, right? Then I want to show you here we have A column, another B column and C column. Okay, then we have output as D, this difference, right? Then the borrowed key. Regarding this, we have 2 outputs. It is difficult to draw 2 outputs in a logic circuit, therefore we have to use K-maps in order to derive a simplified expression for this D column and another K-map for this value. So this value had been fed to this K-map, the borrowed values have been fed to this K-map. Then we will be taking 2 expressions like this. From that 2 expression we will be drawing this logic circuit. So let me explain you further about this scenario using the logician. Here you can see the same thing, A, B, C inputs are there for a full subtractor. A, B, C are there, right? For this A, B, C, I have just created the K-maps. I will explain it to you later. I want to subtract A from B and then from C. It means 0 minus 0 minus 0, right? I want to subtract 0 from 0 again and 0, right? 0 here, again another 0 here, another 0 here. Downwards I want to subtract 0 0 0, 3 zeros downward. So if you subtract 0 from 0, answer is 0. Again if you subtract 0 from 0, answer will be 0. Because of the reason you didn't borrow anything from anywhere, here also it will be 0. Okay, now let me explain this stage. This is pay attention. If you subtract 0 from 0, no problem, it's 0. Then if you are going to subtract from 0 from 1, listen carefully. 0, if you subtract 0 from 0, its answer is okay, 0. 0 minus 1 cannot do. Therefore, you have to 0 minus 1 cannot do, right? From 0 you cannot subtract minus 1. Therefore, you have to borrow a thing. Because you are borrowing, you have to put 1 here. Then, because of the reason we borrowed something here, now the new value in here is 2. 2 minus 1 is 1. Hope you have understood. Then 0 minus 1. Can we do 0 minus 1? In this stage, 0 minus 1 we can't do. So 0 minus 1 we can't do. Then what we have to do is we have to borrow some value. Because of borrowing, I will be putting 1 here because I am borrowing value. Because of the reason I have borrowed, here the value, new value is now 2. 2 minus 1 is 1. Okay. From that 1 minus 0 is 1. Right? Similarly, 0 minus 1 you cannot do. 0 minus 1 you cannot do. You have to borrow. Because of the reason you are borrowing, you have to mark 1 as in the borrow column. When you are borrowing, you are borrowing 2. The value which you borrow is 2 to this place. Then 2 minus 1 is 1. Again 1. Now here we have 1. From this 1 minus 1 is 0. Okay. Here 1 minus 0 is 1. 1 minus 0 is, again we have 1. We didn't borrow anything. Here 1 minus 0 is 1. Right? 1 minus 1 is 0. Therefore both will be 0. We didn't borrow anything. 1 minus 1 is 0. From this one, we will be subtracting this. 1 minus 1 is 0. From that 0, you are going to subtract this 0. Then all together all are 0. Here 1 minus 1 is 0. So now here the new value is 0. Here. From 0, can you subtract 1? Can't, right? You have to borrow a 1. Because of that, I will be putting a 1 here. Now here I have borrowed another 1. Because of that, here now new value is 2. 2 minus 1 is 1. Right? This is the truth table. So similarly, I have to fit these in these columns to this K-map in order to take a simplified expression. Right? So difference column will be fed into this. Borrowed column will be fed into this BC, this borrow column. So initially I have for this difference column 0, 0, 0. Right? It means for the places you have A bar, B bar, C bar, you have to put 0. Here A bar, B bar, C bar. You have to put 0 for that place. Now next one. You have 0, 0, 1 here. If you have combination 0, 0, 1, you have to put 1 there. 0, okay. 0, 0, 1. You have to put 1 there. Then the third column, 0, 1, 0 combination. A is 0 combination. A in 0. A is 0 means this one, this column. Sorry, this row. A is 0 means, oh here A is 0. A 0 means this column. BC. BC is 1, 0. 1, 0 is which one? This one. So if you draw lines, the crossing value comes here. For that place, you have to put 1 because output is 1 here. So similarly, if you fill this one, it will come like this. as a chessboard, as a structure in a chessboard, right? Here 1 1 1 1 as a zigzag shape, 0 1 0 1 like. So if the shapes are in a zigzag shape, right? Chessboard, we call this as chessboard. Chessboard, chessboard shape, right? So we call this as chessboard shape. Because of that, from that we can derive this act as a XOR gate. This total expression act as a XOR gate, right? Thereafter, I have to fill this BC column, ABC column for the borrowed output. Initially, I filled for K-map for this column. Now I'm going to fill K-map for this column, for this. Now I have to see for 0 0 0 we have 0 0 0 0, we have here 0. Then for 0 0 1 combination we have 1 0 0 1, 0 is this one, 0 1 is this one, 0 0 1. For combination we have 1. Similarly, if you fill this gap, you will have an output like this. So in this case, we cannot group any values 2 by 2 or 4 by 4. We have to group this one individually, this one and this one. In this case, we can group this one like this, right? And again like this, and these two, and these two, and these two, 2 by 2. This one and this one, and again this square and this square, and again this square and this square. From that we can generate ABC expression. After generating only, you saw this one, you can see here, you can circle this one, and you can generate the expression for this circuit. And from here you can generate the other expression considering the Karnaugh map. The expression is in here, right? After creating that expression, from that expression we will be designing this full substractor logic circuit. Let me go into that circuit now. So I need 2 OR gates, right? Initially I'll take 1 OR gate and I'll show you some kind of a explain you some kind of a scenario in here. So I'll be taking one I need XOR gate because this is XOR. I am reducing the number of inputs as 2, right? So that XOR gate is okay. I need another AND gate. I'm going to reduce the inputs to 2, and I need NOT gate. I'll be connecting this one, keeping it here, taking this one, and I'll be extending these lines. So initially how I'm going to do this one is I'm going to construct half subtractor circuit, right? From half subtractor circuit I'm going to derive the full subtractor circuit. Now I have half subtractor circuit, right? This is the half subtractor circuit which you saw in the prior video. Now for full subtractor circuit, I'm gonna make this as twice. I'm gonna select this one. I'm gonna copy the selection and I'm gonna paste it again. From edit, paste. Now I have two half subtractor circuits, right? I have two half subtractor circuit now. So I'm gonna connect, right? I'm gonna connect this one to here with this circuit to this circuit. I'm gonna add two subtractor circuit together and I'm gonna form another circuit. So I'm gonna extend this one up to here, and then the output which comes from this line, right? Uh, the output should be connected to this one. These two ends should be connected. Because of that, I will be shifting this one a little bit downward. Oh, okay. This one need to be connected like this, and this input should come like this. So I am connecting two half subtractor circuits together. This is a one half subtractor circuit. This is another one. So I have connected output of this one to this, right? So for this one, the input is I am going to change the input to this one, right? One input as this, and this one should be connected to the upper one, just the reciprocal of this one. Earlier for the half circuit, this is for here, the NOT gate comes for upper one, the other one for this one, but in this case the NOT gate should come to this one, output of this one, and then it should go, the other one should be go to the up one, right? So now okay, now my circuit is okay, and I need another OR gate. For here, I'm going to reduce the number of inputs to 2, and I'll connect this one, and the output which comes from here, I like to connect it to this stage and take the output from here and take the output from here also. And I'm gonna add a pin to this place like this, right? Then my circuit is almost completed. Then I need to add inputs for this one, right? This is the input A, this is B, and the top one is C, right? This is A, this input is B, and this is C. So I want to take the C to this side in order to simulate it. It is easy to simulate if I make it at that point. So what I'm gonna do now is okay. Now I'm gonna rename this one as A, B, C, right? I have renamed it, right? Now almost my circuit is completed actually. So let me show you the previous. Here you can see the same thing I have created in there, right? So this one is this output is difference. This output is borrow. So you can see the difference output from this one and the borrowed output from this value, this thing. Now I have created my full subtractor using logic gates. Also I can create, rather than creating from the logic gate, I can create it from the from here. You can take this piece of circuit and just place it here. It's easy. Then double click on that, reduce the number of bits as 1. Then you have to do is you have to take the inputs like this. This is the input A, this is input B, and this is the input C. A input, B input, and C input, and you will have difference and the borrowed value. So I'm adding a pin here. I need another pin in here. I'll change the direction to south, heading towards south. Okay, now I'll name these items now. This as A, this as B, this as C, and this is my difference. This is my borrowed. Now my 2 circuits are completed. Now I'm going to simulate these 2 circuits. Let me start the simulation. Right. I'm choosing this hand tool. If I choose this hand tool now, okay. The inputs are 0, 0, 0. When the inputs are 0, 0, 0, outputs are 0, 0. It's okay. Here inputs 0, 0, 0, output 0, 0. Input 0, 0, 0, output 0, 0. When the inputs are 0, 0, 1, 0, 0, 1, 0, 0, 1. These both circuits are same, okay. Now you can see inputs are 0, 0, 1, 0, 0, 1. Output should be 1 and 1, 1 and 1. Satisfied? 1 and 1. When the input is 0, 1, 0, 0, okay, 1, okay, 0, 0, 1, 0. You can see then also the both outputs are 1 and 1. The stage is correct. When the inputs are 0, 1, 1, 0, 1, 1, 0, 1, 1. You can see output is, for the difference we have 0, other thing 1. Difference 0, other thing 1. Borrowed 1 is 1. 0, 1 output we have, 0, 1 output, okay. When the inputs are 1, 0, 0, 1, 0, 0. 1 0 0. We have 1 0 as the output. It's correct, right? Again 1 0 1 1 0 1 1 0 1. Both are 0 0. Both are 0 0. It's correct. Again 1 1 0 1 1 0 1 1 0. If inputs are 1 1 0, output is 0 0. You can see from the board circuit it's 0 0. If the all inputs are high now, it should be 1 and 1. You can see it's proved it's 1 and 1. Here what has happened is, let me explain you again. Right? If you choose this row 1 0 1 1 0 1 1 0 1 combination. So if you choose 1 0 1, you have 0 0 as the output. How it is possible? Let me explain you. 1 0 1. You are going to subtract 1 1 minus 0. What is the answer for 1 minus 0? It's 1, right? From that one, you are going to subtract another one. 1 minus 1. What is the answer? Final answer should be 0. Final answer should be 0. The final answer is here, 0. Because we didn't borrow anything from somewhere, the borrow value is 0. This is the working principle of full subtractor with the logic gates, and also using the circuit which is already created, pre-created circuits. So hope you have understood everything very well. So let's meet up from another tutorial. Until then, thank you all.